Hi there, and welcome back to the Formulaic Approach channel. In this video, we are going to be talking about electric field due to a dipole. We have seen electric field due to monopoles before, so this time we want to see electric field due to a dipole, okay? Now, you have to first understand what a dipole is, okay? So a dipole is, the word di means two, then pole there refers to the charges, okay? So when a system contains opposite polarity, two different charges, or when a molecule contains two different charges, in that molecule, there exists a dipole. Is that clear? That is, there are two opposite charges, the positive and negative charges, on a molecule or in a system or in space, wherever that is what we call a dipole, okay? Two opposite poles. Now, you also have to understand what is called dipole moment. Now, the dipole moment is actually the vector product of the charge and the distance of any of the charges in a dipole. Is that okay? So I've defined dipole, and now I'm defining dipole moment just to keep track of the things that we are learning. Okay, so I said a dipole moment is basically the product, the vector product actually, of the electric charge of any of the dipole, the magnitude of the electric charge of any of the dipoles, and the distance between the dipole, the distance of separation of the dipole. We basically use the dipole moment to measure the degree of, would I say, evenness in distribution, how evenly distributed a charge is within a molecule or a system, wherever that is again. And I have already talked about charge distribution and straight line and a lot of those other conformations. So dipole moment is basically the measure of how evenly distributed the charge is in a system. But mathematically, it's the vector product of the charge and the distance of separation between the dipole. Why? Because it also shows it is directional. Is that clear? It is directional. Moment is a vector quantity, so that's why dipole moment is going to be a vector quantity. All right. So let's go into the mathematics. All right. Electric field due to a dipole. We are going to be examining two phenomena rather, where we have at an axial point of the dipole. So we may want to examine the electric field due to a dipole at a point that is at an axial point on the dipole. That is, it is collinear with the dipoles, the line of dipole, the line of separation of the dipole. That point where we are going to be calculating the electric field from is going to be a collinear point with the dipole, the two charges. Then we can also calculate the electric field due to a dipole at a point that is now on the perpendicular bisector of the dipole. Diagrammatically, okay, diagrammatically, let me show you. So we have a charge here, positive charge, and another charge here, a negative charge, okay? So this is a dipole here. Now the distance of separation between them, okay? Let's call that A. So if that is A, I mean the distance of separation between them rather is 2A, let's call it 2A. Okay, we want to call it 2A, which means that from a midpoint M here, let's use this line to join them, so that this point will be midpoint M. Then the distance from here to here is going to be 2A, which means that from here to the midpoint M, we are going to have the distance to be A. And from another point, from this middle again, to the second charge, we're going to have what? A. So the entire length of the distance of separation is 2A. Does that make sense to you? Okay, so we want to calculate the electric field due to this dipole first at a point that is collinear with this line. Okay, so at a particular point, let's call this point P as we have been using. So these are point P, okay, that is at the axial point of our dipole. Does that make sense? All right, so this P also is going to be at a distance between this guy and this guy, but we are usually considering the distance between this point P and the middle, where it seems as though the electric field were to be emanating from. First, the reason it's so is because the magnitude of this charge and the magnitude of this charge are equal. So the magnitudes are equal, only that their signs are different. When they are placed like this midpoint M is going to be the point where it would seem as though the electric field were emanating from, due to a charge were emanating from. Does that make sense? Okay? Even though we know that the electric field that will be felt here is going to be the sum of the electric field due to charge 1 and the electric field due to charge 2. Dipole. Okay, then I also said dipole moment. Okay, dipole moment is equal to Q cross R. Does that make sense? Q cross R. Okay. It's measured in dBi. But anyways, we're not going to be talking about the units so much here. I just wanted you to see this. Now, where R is going to be our distance, well, because we are using A here as our distance, then we are going to be using this R as the distance between the points and the point, not the distance of separation now. So let me change this to A, since we are using A for the distance of separation. Does that make sense? I changed it. R is the distance we've been using for, you remember, as we have been, since we've been seeing the electric field and Coulomb's law. R is the distance of separation from the electric field, as we've been doing, to a particular point, okay? So that we will not misplace those quantities, or those, what we use to denote them, okay? All right. The electric dipole is denoted by, we use P to represent it. Exactly, capital P to represent electric dipole. Okay? All right. So just follow me. I'm being slow because of the weather. But of course, I also want you to get every little detail of what I want to explain. So we want to calculate the electric field at this point due to this dipole. I mean, of course, the electric field at this point is going to be the sum of the electric field due to these two poles, these two electric charges. Now listen, the same. The distance of separation from here to here. Why are we making reference to this? I've said it because it's going to seem as though the electric field is emanating from that point, because the magnitude of this guy is equal. So the distance of separation is going to be x. We will call it x. We're going to call it x. Why? Because we want it that way. All right, because we want it that way. Now, so electric field due to, let's call this charge 1 and charge 2. So electric field 1 will be equal to what? KQ1 over R squared. Does that make sense? Okay. Now you know that here, our R is going to be affected. Why? Because our R is going to be from this place to this place. Does that make sense? Yes. So what does that mean? If from here to here is A, from here to here is A, and from here to here is X. Therefore, for E1, comma, R is going to be X plus A. Does this make sense? I'm gonna explain again. I said that if from here to here is, if from here to here is 2A, and from here to here, where we are feeling the electric field, point P, is X. It means that half of this distance, half of 2A, is going to be A. Okay? So A and this entire length, that's going to be X plus the remaining A. Does that make sense? Good. So we can therefore say that E1 is going to be what? KQ1 over R squared. In this case, is going to be what? X plus A all squared. So if you wanted it, you know that K is already 1 over 4 pi epsilon naught. So you can say that E1 is going to be what? Q1 over 4 pi epsilon naught X plus A squared. I hope you are not confused at all here. Okay. Now, what is going to be E2? That is electric field due to charge 2. It's also going to be the Q2 K multiplied by Q2 over R squared. This makes sense here from what we've been doing. This one is R1 squared, this is going to be R2. Recall that for E2, R2 is going to be from here to here. If from here to here is X, okay, and from here to here is A, it means that the remaining, when we subtract, if this entire place is X, and from here to here is just A, which is half of this, then it means that the remaining will be X minus A. Remember, it will not be half of X. I've seen someone mistakenly say it will be half of X. I only drew my own this way because, okay, for example, let me shift my point P away, as far away as possible from my dipole. So you can already tell now that my distance Q2 away from this guy is not going to be half of X. Does that make sense? All right, if this is the case, then E sub 2 becomes K, which will now be 1 over 4 pi epsilon naught, to be Q2 over 4 pi epsilon naught R squared, out with this guy, X minus A all squared. Okay. Now recall that I said that the sum of electric field here, or the electric field on this guy, E, is going to be the sum of E1 plus E2. Does that make sense? All right. But now, we have some analysis to make. Now, E1 is going to act in what direction? E1 is going to act in this direction, isn't it? Okay. Now, E2 is going to act in this direction. In which direction? E2 is going to act in the opposite direction. Do you understand why? If you understand why before I say it, you can put it in the comment section. But let me explain already. Now, E2 is going to be is going to be in this direction because, now listen, because for a negative charge, the line of the electric field lines are going to be pointing inwards. Does that make sense? It's going to be pointing inwards. So because of that, electric field due to charge 2 is going to what? Inwards. It's going to be inwards. Let me take water. It's going to be inwards, and electric field due to charge 1 is going to be what? Outward. Does that make sense? So if they have different directions, what does that mean? Our E is going to be what? E1 plus negative E2. Remember, they are what? Vectors. Okay. So what does that mean? That E therefore will be what? E1 minus E2. I hope this is clear. Once this is clear, we can therefore go on to saying that E is going to be equal to E1, which we got to be this, Q over 4 pi epsilon naught X plus A all squared minus Q over 4 pi epsilon naught X minus A all squared. I hope this is clear. Simple, basic mathematics. Okay, if this be the case, let's take the LCM or LCD, lowest common denominator, and then we're going to have our E to be equal to, our LCD is going to be 4 pi epsilon naught, which is already common, multiplied by x plus a all squared, multiplied by x minus a all squared, okay? So if you take this, if you multiply this LCD by this guy, what are you going to be left with? You're going to be left with this guy. Does that make sense? So we have Q, which will be multiplying x minus a all squared. Does this make sense? Then minus, if you multiply this guy by this denominator also, I'm going to be left with this guy, which means we have Q into bracket x plus a all squared. Does this make sense? I hope you're following me. Then we have that E will be equal to, Q is common, so how about we factor it out? So if we factor out Q, then we'll have Q into bracket x, so let's open a curly bracket this time. So into bracket x minus a all squared minus x plus a all squared. And we close our curly bracket over 4 pi epsilon naught. Now let me do something here. You know that if I have a minus b and a plus b as difference of two squares, you remember that it will be what? A squared minus b squared, okay? All right. So in this case too, if I have x plus a all squared and x minus a all squared, you know it is the same as x plus a and x minus a both squared. This makes sense, right? Because this is squared, so we can say both of them multiplying each other squared, okay? So when you have this, it has turned to what? Difference of two squares, right? So we can already say that it is what? X minus x squared minus a squared, then all squared. Do you agree with this? If you don't understand, rewind it to what I said here. Very simply, difference of two squares turned to this. So we converted this to this so that we have difference of two squares all squared. So we have x squared minus a squared all squared. Does that make sense? Thank you. So the next thing we are going to be doing is expanding each of these. So by the time we expand this, we have E equal to Q into bracket. Expand this, we have x squared minus 2 times x times a. That will be minus 2ax. I hope you understand what I did. To expand squares, just take square of this, then the sign, which in this case is minus, then the sign, then you now multiply 2 times x times a. Does that make sense? Then, if you now take the square of minus a, that gives you plus a squared. Does that make sense? All right, let's use the same idea here. X squared, yeah? Then plus 2ax plus 2ax, then plus 2ax plus 2ax, then you square this plus a squared. Sorry, I was thinking of something. So all over 4 pi epsilon naught x squared minus a squared all squared. I hope I'm not too fast. Okay, so E therefore becomes Q into brackets. By the time we open these brackets, we're going to have x squared minus 2ax plus a squared minus, we open the bracket, minus x squared minus 2ax minus a squared. All right. So if you can already see, you will notice that this will take care of this. This will take care of this. So we have minus 2ax minus 2ax. Okay? All right? So minus 2ax minus 2ax. Let's say we are dealing with only the numerator now. Only the numerator. So we are going to have q into bracket minus 2ax minus 2ax is going to be minus 4ax. Okay, we are going to neglect the negative because it is electric field. So this might just be direction. Okay? It's just signifying direction, okay? So, or let's just neglect it because it doesn't really affect our equation in this case. So over 4 pi epsilon naught over x squared minus a squared all squared, okay? So by eyeballing this guy here, by eyeballing our guy here, our numerator over denominator, so over denominator here, our formula becomes E equals to Q into bracket 4AX. That will be 4AX cubed. I hope this makes sense. Over 4 pi epsilon naught x squared minus a squared all squared. Okay? Now there are two things I want to introduce here. Now you know that the distance of separation between our two charges is 2a. Does that make sense? Okay. So our dipole moment here is going to be 2a, which is the distance, times q. Does that make sense? All right. So if p therefore is 2aq, according to this question, if the distance of separation is 2a, then we can therefore say that 2aq, by the time we factor out 2aq here, e is going to be 2. You know, this will be 2 multiplied by 2aq times x. 2aq, I brought this and this out, and this is my x, and this is my 4. Does that make sense? All over 4 pi epsilon naught x squared minus a squared all squared. So this is going to be my dipole. So I can introduce this into my equation, and then it becomes E equal to 2px all over 4 pi epsilon naught x squared minus a squared all squared. Does this make sense? All right. Now you also know, let me introduce another thing. If the distance we chose for P, the point rather we chose for P, is infinitely large. Now I just mean very large, not infinitely. It means that this subtraction here, if you subtract, say, 2 from 1,000 and you square it, it's almost the same as squaring 1,000. Does that make sense? Because this is going to give you 998. 998 squared is going to be close, very, very close to 1,000 squared. I hope that is clear to you. Okay? So if that is clear, then you will understand what I mean when I say that for x, for the case where x is very much greater than a, then our electric field is going to be 2px, that is 2 times dipole moment times distance over 4 pi epsilon naught x squared. Okay? Okay, sorry. X squared times 2, because it's squared. Okay? X squared squared. That's going to be x raised to power 4. Okay, then x can now cancel x, yeah? So that E becomes 2p over 4 pi epsilon naught x cubed. And this is going to be our electric field at an axial point from our dipole. I hope that is clear. All right. Now let's see electric field at a point on a perpendicular bisector of dipole. So let me just clean my, so we're no longer dealing with that point, we're now dealing with this point. A point that is at a perpendicular bisector P, like this. Okay? Want to check the electric field due to this and due to this. Does this make sense? No. Let me draw it in another conformation. Let me change the conformation. You see that we are still talking about the same thing, okay? Okay? So let me put my positive charge here and my negative charge here, and they are separated by distance 2a still, right? So that there is a point M here, where from here to here is going to be A, and from here to here is going to be A. Now we are now calculating the electric field due to a point P that is on the perpendicular bisector. So this is our perpendicular bisector, this point here. Does that make sense? So this distance away here is going to be X. Does that make sense? So electric field due to this Q is going to act along this line. Does that make sense? Electric field due to, let's call this Q1 and Q2. Electric field due to Q2 is going to act along this point. Does that make sense? Yes, 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 yes. All right, let's go. Now, we need to now bring our coordinate system here so that because Q1 is positive, what will it do? What does positive do? Electric field line is going to be radially outward, right? So because of that, this will be what? Outward in this direction. Okay? Then this guy for Q2 is negative, is going to be what? Radially inward. What does that mean? Radially inward. So this will be E1, electric field due to charge 1, and this will be electric field due to charge 2. Does that make sense? So it's going to make an angle theta here and an angle theta here. And because it is at a perpendicular bisector, theta 1 will be equal to theta 2. That makes sense mathematically, yeah? Okay. Okay. All right. So what do we want to do now? We are going to be having to resolve into horizontal direction and horizontal component and vertical component. But you see, I've got you covered because in this case, it's very simple. Our x components are going to cancel out. Why? Because E1 component, when we resolve it to this direction, is going to be positive. Our E2 component, when you resolve to this direction, is going to be negative. And since both of them are equal in magnitude, electric field due to both on the x-axis is going to cancel out. So we call that symmetry. Do you remember? Symmetry. So there's going to be a cancellation of both axes due to symmetry, so that sum of electric field on this at point P is going to be just the one due to what? The y-axis. Of course, it's going to be negative y-axis here, but we can already eyeball it also because it's going to be double negative. Does that make sense? All right. Okay. So also here, our electric field is going to be equal to E1 plus E2. But the point is now that E1 is actually due to our E rather, is actually, sorry, I didn't write that well. Yeah, this is the same thing, it's the same thing. So E is going to be E1 cos theta. This place is going to be our E. I said electric field, sum of electric field is going to be just the Y component. Does that make sense? Y component. So E is going to be E1, close the angle, that's cos, right? Just remember, C to C, close angle. Then open angle, sine, sin, sine. I've proved that to you, proven that to you before, how it is so. So, but I assume you already know that. So E1 cos theta plus E2 cos theta. Okay. Now, since E1 and E2 are going to be exactly the same, because if you look at it here, this guy is at a perpendicular bisector. What does that mean? It means that it's going to give you at least an isosceles triangle. There might be a point where it will give you a collateral triangle, probably. But at every point that is a perpendicular bisector, whether here, or here, you're always going to get an isosceles triangle. What does that mean? This line here, this distance here, are going to be equal. So what that means is that E1 cos theta is going to be E2 cos theta. Does that make sense? So that E1, or our E, is going to be 2 E1 cos theta, or 2 E2 cos theta, since E1 and E2 are going to be the same. I've told you the reason, magnitude of charges at the same distance apart, at the same. Do you understand now? All right. Okay. Now, how do we get this distance or this distance? How do we do that? So let's call it R. So if this is our right angle, using Pythagoras rule, we know that R will be equal to square root of, this is our hypotenuse, right? Square root of a squared plus adjacent, x squared. So square root of x squared plus a squared. Is this clear? God bless you. So what that means is that our E is going to be 2 multiplied by E1 cosine of theta. Now, what is cos theta? I was going to write about cos theta, so let me just write cos theta. Okay, no. Recall that cos theta is adjacent over hypotenuse, right? What's our adjacent here? It's going to be with respect to this angle. Yes, okay? Because the angle is going to change. And that was probably what I said. The angle is going to change. The angle is going to change as this distance is moving. So that's why your cos theta is going to be with respect to this angle. So that your adjacent is going to be this side, which is already A. Okay? So cos theta is going to be A over, the hypotenuse is this guy, which is root x squared plus A squared. So we can impute that into the equation and say that this is going to be multiplied by A over square root of x squared plus A squared. I'm going to clean this part now. So from here, we can now say that since E is going to be Q over 4 pi epsilon naught over R squared, and what's going to be our R? Our R in this case. You know that this place is our R, right? Okay, it's already there. So, it's already there. So, E will be equal to, yes, 2 multiplied by Q over 4 pi epsilon naught over R squared dot A over the square root of x squared plus A squared. Now, since this is R squared, not R, if R is equal to this, then R squared will be equal to what? X squared plus A squared, since R is square root, right? Okay, so we can easily say that E equal to 2Q over 4 pi epsilon naught R squared, which is X squared plus A squared, multiplied by A over square root of X squared plus A squared. All right, so here we can bring them together and say that 2AQ over 4 pi epsilon naught. Okay, this is going to be I don't know, x squared plus A squared. Okay, all raised to power 1 times x squared plus A squared raised to power half. Does that make sense? So we now use indices. We now use indices. So that E is going to be 2AQ, okay, all over 4 pi epsilon naught x squared plus A squared all raised to power 1 plus half. That will be 3 over 2. That will be 1 over 1 over 2, right? Okay. Remember that our dipole moment P is the distance times charge. And our distance here is already 2A, right? So 2A times Q. So it means that P is 2A times Q. Does that make sense? Are you loving it? Tell me you are loving it in the comment section. So it was 2aq, which is already p, over 4 pi epsilon naught x squared plus a squared raised by 3 over 2. So this is for the case, for this kind of case. What if we chose a point that is infinitely long, such that x is so long that a cannot catch up with it? The same idea we hold. It means that a will be, the value, the contribution of a will be almost insignificant, yeah? So it means that it can turn to e equal to p over 4 pi, that is 4, x very, very greater than a. So it can turn to 4 pi epsilon naught over x squared raised to power 3 over 2. Does this make sense? All right. Because a is very, very small or insignificant in this case. So e equal to p over 4 pi epsilon naught. Now, this will be 2 multiplied by 3 over 2. Does this make sense? You like that, yeah? So that becomes x raised to power 3. And that will be the electric field due to a dipole at a point on the perpendicular bisector of the dipole. Please do well to subscribe to the channel and share the video with your friends, and you're going to see that God is going to bless you. Amen.